Assalamualaikum warahmatullahi taala wabarakatuh. My name is Ilham bin Abdullah. My matrix number DF250004. And today, me and my friend from Group 6, Section 2 will be presenting our project titled Evaluation of Drain Constriction. This project is for our hydraulic course, and we would like to thank our lecturer Dr. Wan Afnizan bin Wan Muhammad for his guidance. Let us begin.
Hi, I'm Dinesh. My matric number is DF25003
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Aiman Alif bin Amri and my number matric is DF250013.
Hi, my name is Yugin Morgan. My matric number is DF250083.
So now we want to present our project on a campus drainage system at University Tun Hussein on Malaysia. Good drainage is important to prevent flooding, but narrow path in a drain can block water flow. In this project, we study a local campus drain that changed into an underground culvert. We measure the drain and calculate how water flow through it. Our main goal is to check for any flooding risk and make sure the campus drainage system works well and stay safe. Now, let us look at our methodology. Our work was divided into two main parts. First, we went to the UTHM campus site to physically measure the size of the drain and the narrow culvert section. Second, we use the measurement to calculate different water flow parameters like uniform depth, critical depth, and specific energy using standard formula and a fixed flow rate.
Alright, so I will explain about the slide 2.2 tool and equipment. So first, measuring tape used to measure the physical dimension of the open channel, include the bottom weight, depth and the weight of the constriction. So two smartphone camera used to capture photographic evidence of the drainage profile and the group activity for the appendix. So 3 file notebook used to document all raw data and observation on site. Okay, so I will explain the next slide. Slide is 2.35 procedure. So first, site identification was carried out. The drainage channel and covered location were identified and the safety inspection was conducted before starting the measurement. Next, the channel condition was inspected. The channel lining and slope, or SO, we are checking manning roughness, was taken as 0.025 for the stone masonry section and 0.013 for the concrete culvert. Okay, then flow observation of performance. The flow direction was observed to determine the upstream and downstream section of the channel. After that, the flow depth was measured. The existing water depth was measured vertically from the channel bed to the water surface. The open channel dimension were also measured. The measuring that was used to determine the channel bottom width and the channel depth. Finally, the covered constriction width B was measured to obtain the required dimension for the hydraulic analysis. Alright.
Now I'm going to talk about the hydraulic equation. The uniform flow analysis. Normal depth YO. The formula is Q equal to 1 over NAR 2 per 3 S not 1 over 2. Q is equal to design of flow rate 0.25 meter cube per second. N is manning coefficient. A is cross-sectional area meter squared. P is water parameter. R is hydraulic radius. A per P and S naught is bed slope. Secondly, critical flow analysis. Critical depth YC formula is q squared times t over g times a cube equal to 1. So t equal to top surface width, the gravitational acceleration equal to g equal to 9.81 meter per second squared. Now I'm going to talk about the hydraulic equation 2.4. State of upstream flow. Compare your computed uniform depth YO against the critical depth YC. If Y naught is more than YC, it is stated subcritical flow. By the way, if Y naught is smaller than YC, it is stated supercritical flow. And number 4 is the maximum width Bmax. Formula is E naught equal to Y naught plus Q squared over 2GA 1 squared. For rectangular constriction, we mean equal to 3 over 2 YC2. Thus, 3 over 2 square root of Q over B max squared over G equal to E naught. The B max equal to square root Q squared over G 2 over 3 E1 cube. 2.4 Hydraulic equation. 5. Classification of flow transition cases. The measured constriction width B is compared with the maximum allowable width B max to classify the flow into three transition cases: non-choking flow, critical flow, and choking flow, which causes an upstream water level rises. Number 6, I'm going to talk about the calculation of water surface profiles across the constriction. Once the transition case is identified, the water surface profile is determined by calculating the flow depth at the upstream Y1, constricted Y2, and downstream Y3 sections using the specific energy equation to show the overall water level variation.
For the next parts, let's move on to the sample calculation. So the picture is explaining the rectangular and trapezoidal measurement for our project, and the given value is Q equals to 0.25 meter cube per second, and the Manning roughness N equals to 0.013, and the SO equals to 0.015, and the side slope Z equals to 1 over 10 65.38. So the Z value is 0.46. This means the slope is 1 per vertical and 0.46 by horizontal. For this part, I'll explain how we find our uniform flow depth YO, which is we use the Manning formula Q equals to 1 over N AR 2 over 3 SO 1 over 2. For the area, we got B times with YO plus B times with YO plus Z times with YO square equals to 3.5 YO plus 3.5 YO plus 0.46 YO square. And for the wetted perimeter P equals to B plus 2 YO square root 1 plus Z square. So 3.5 plus with 2 times with YO square root 1 plus 0.46 square. And after we rearrange the Manning formula, we got 1 AR 2 over 3 QN over SO 1 over square. So after rearranging the formula, the last formula is 3.5 times with YO plus 0.46 square 5 over 3 over 3.5 plus 2 YO square root 1 plus 0.46 square 2 over 3, and equals to 0.25 times with 0.015 equals to 0.0015. So through trial and error YO, we got 0.8584 meter. For calculating critical depth YC, we use Q square T over G AC square equals to 1. For the G value is 9.81 ms square, and the TC equals to 3.5 plus 2 times is 0.46 YC, and the critical area AC equals to 3.5 YC plus 0.46 YC square. After rearranging the formula, we got YC equals to 0.0801 meter. The next part is determination of upstream flow state. The first is normal flow area AO, which is 3.5 times is 0.8584 plus width 0.46 times width 0.8584 square. So the area is 3.1603 meter square. And for the normal top width, TO equals to 3.5 plus 2 times is 0.46 times is 0.8584. So the T is 4.2897 meter. And for the hydraulic depth, which is D, AO over TO, which is 3.1603 over 4.2897. So the D is 0.7367 meter, and for the D flow velocity VO equals to Q over AO, which is 0.25 over 3.1603. So the VO is 0.0791 meter per second, and flow number effort equals to VO over square root GD, which is 0.0791 over 2.688. So the effort value is 0.0294, and the flow classification is, since effort is lower than 1, which is 0.0294 is lower than 1, so the upstream value is subcritical flow. For the fourth part, determination of maximum bit or constriction Bmax, the first formula is upstream specific energy EO. EO equals to YO plus VO square over 2G. So the EO value after substitution is 0.8587 meter. For critical flow at constriction, E mean square equals to 3 over 2 YC square equals to 0.8587 meter. So YC square equals to 0.2 2 over 3, 3 over 2, 0.8587. So the YC square equals to 1.2881 meter. For a rectangular constriction, QC equals to square root YG YC square power of 3. So the QC value is 4.5789 meter cube per second. So for the Bmax, the formula is Q over QC. So 0.25 over 4.5789. So the Bmax value for the constriction is 0.0546 meter. So the last part for the calculation is determination of flow case. The measured constriction weight is B2 equals to 3.5 meter, and if we compare with Bmax, which is 0.0546 meter. So the B2 value is bigger than Bmax, which is 3.5 meter, higher than 0.0546 meter. The constriction is larger than the critical void. Therefore, the flow follows case 1. It does not experience any choking. So the flow case for this constriction is case 1. For the flow depth determination, the upstream depth y1 and downstream depth y3 for case 1 are given by y1 equals to yo equals to y3. Therefore, the y1 and y3 value is 0.8584 meter. For the constant depth y2, we need to calculate by using the formula q2 equals to q over b2, which is 0.25 over 3.5. So the value of q is 0.0713 meter square per second. Since E2 equals to EO, the y2 plus q square over 2g y2 square equals to EO. So the y2 value is 0.0583 meter. So these are the result we got from our project. So the location we got is before Faculty of Technical and Vocational Education, and the Q value which were given is 0.25 meter power of 3 per second, and longitudinal SO equals to 0.015, and the channel lining is stone pitching, and the Manning roughness coefficient is 0.013. And based on our result, the depth of uniform flow YO we got is 0.8584 meter, and for the YC we got 0.0801 meter, and the upstream value is subcritical flow, and the maximum bit of constriction which will start to produce critical flow B is 0.0546 meter, and the case of flow through constriction is case 1, and the depth of flow, which is y1 equals to y3 is 0.8584 meter, and the y2 is 0.8583 meter.
In conclusion, this project successfully evaluated the water flow characteristic of the drain at Utachim. We found that the water flow is subcritical because the normal depth is greater than the critical depth. The drain operates smoothly without choking because its actual width is much larger than the narrowest limit, which prevent water from backing up. Ultimately, the current drainage system has enough capacity to handle heavy rainfall efficiently and eliminate any risk of flooding upstream.
And these are the appendix for our project. The first photo is identifying of the drain, constriction or box culvert site location. And the second picture is measuring the base width of open channel B equals to 3.5 using a measuring tape, and the last picture is measuring the height of the open channel.